we've talked about the fastest, heaviest planes. So today, let's talk about the heaviest plane ever built during World War II. That's the Bv-238, weighing in at a staggering 110 tons. This giant German flying boat boasts a wingspan of 60 meters, surpassing even the B-52 Stratofortress. Powered by 6 Daimler-Benz DB 603 GS engines, each producing 1,900 HP, this engineering marvel could transport up to 300 troops and carry nearly 90,000 pounds of supplies across an impressive range of 4,110 miles. Although only one prototype was completed in 1944, the Bv-238's development represented a significant leap in aviation engineering. Initially conceived as a 4-engine transport plane in 1941, it evolved to serve multiple roles, including long-range Sea Scout, transport, and bomber. The aircraft's remarkable specifications and versatile design capabilities made it a unique achievement in aviation history. Despite its brief existence, now we will look back at its great specifications. The genesis of Bv-238 engineering vision. The smaller but still substantial Bv-222 Viking. The aircraft's journey started as a 4-engine transport plane intended for civilian use. Nevertheless, Germany's wartime circumstances prompted a significant shift in the project's direction. The original Powerplant choice consisted of 4 24-cylinder GM-223 engines. However, when these became unavailable, engineers adapted the design to accommodate 6 12-cylinder Daimler-Benz motors. The design philosophy behind the giant aircraft was rooted in practical manufacturing considerations. The engineering team focused on efficiency and functionality, incorporating features like a tubular steel wing mainspar that also served as an armored fuel tank. The aircraft also had an unusually long and slim planing bottom, with a 2-step design, enhancing its stability and performance. Additionally, its cavernous interior was made easily accessible through a large nose door, allowing for quick loading and unloading. The Bv-238's design objectives expanded significantly as military requirements evolved. The aircraft was engineered to serve multiple roles, including maritime patrol, transport operations, and potential bomb missions. Furthermore, the design incorporated passages within the wings, enabling crew members to access engines during flight. The engineering team's ambitious vision manifested in the aircraft's remarkable specifications. At 60 meters, its wingspan surpassed that of the B-52 Stratofortress. Additionally, when fully loaded, the aircraft weighed 110 tons, securing its position as the heaviest aircraft of its time. To validate the innovative design concepts, particularly the long and slim hull configuration, engineers commissioned a quarter-scale model. Consequently, this testing phase, though delayed by wartime pressures, demonstrated the team's commitment to thorough engineering validation. Revolutionary size and structure. Standing as a testament to German engineering prowess, the Bv-238's massive structure redefined the aircraft design limitations of its era. The aircraft's colossal dimensions included a wingspan of 60 meters, notably surpassing contemporary bombers like the B-17 Flying Fortress, so much so that the B-17s could park side by side on its wings. The Bv-238's wingspan set new records in aviation design, reaching an astounding 17 meters. This impressive size not only surpassed contemporary aircraft standards but also established a new benchmark for the design of large flying machines. To put its scale in perspective, the Bv-238's wingspan was significantly larger than even some of today's modern military aircraft, such as the B-52 Stratofortress. This vast wingspan provided the necessary lift to support the aircraft's massive size and heavy payload capacity, making it a groundbreaking achievement in aviation engineering. In terms of overall dimensions, the Bv-238 measured 43.36 meters in length and 13 40 meters in height, further emphasizing the enormity of the aircraft. These measurements, combined with its wingspan, contributed to its formidable presence, making it one of the most impressive flying boats ever constructed. The structural engineering challenges involved in designing such a massive aircraft were formidable. The engineering team had to develop several innovative solutions to ensure that the BV-238 was not only large but also functional and efficient. One of the key features was the sophisticated two-deck configuration, which maximized the interior space. The upper deck was used to house the crew and various inboard equipment, ensuring smooth operation during flight. Meanwhile, the lower deck was designed as a storage area, capable of accommodating up to 150 soldiers, making it a versatile transport aircraft. Additionally, the large front hatch door allowed for quick and efficient loading and unloading of cargo, which was essential for military operations. The aircraft's wings were supported by tubular main spars, a structural innovation that added strength and stability to the wings, allowing them to bear the immense weight of the aircraft and its cargo. These engineering solutions combined to make the BV-238 an extraordinary feat of design and construction, capable of carrying heavy loads over long distances with remarkable efficiency. The weight management system represented a masterpiece of engineering calculation. The MP weight stood at 54,700 kilograms, specifically distributed across the massive frame. The engineers incorporated passageways within the wings, enabling in-flight access to the 6 engines. The aircraft's structural integrity relied on advanced materials and innovative design choices. Notably, the wings served multiple purposes beyond providing lift. They housed additional fuel tanks and oil storage. The trailing edge incorporated specialized flaps, ensuring optimal control despite the unprecedented size. The maximum takeoff weight reached 85,000 kilograms, requiring careful consideration of load distribution. Accordingly, the engineers implemented a sophisticated hull design, featuring a 2-step configuration, ensuring stable water operations notwithstanding the massive size. The structural design prioritized practical functionality. The wing construction specifically allowed maintenance crews to access engines during flight through built-in passageways, an innovative solution for maintaining such a large aircraft. Moreover, the fuselage design incorporated reinforced sections to handle the immense stress of water landings and takeoffs. Powerplant engineering marvel. First of all, the powerplant configuration of the BV-238 represented a remarkable feat of engineering adaptation. The aircraft's final design incorporated 6 Daimler-Benz DB 603 GS liquid-cooled inverted V1 piston engines, marking a significant departure from its original concept. The engineering development of the BV-238 began with the intention of using Frejumol 223 diesel engines, a design choice that quickly proved to be inadequate for the massive aircraft. Recognizing the limitations of the initial engine selection, the design team embarked on a major overhaul of the power system. In July 1941, the result was a significant redesign that ultimately saw the addition of 6 engines, arranged in nacelles along the leading edge of the aircraft's wings. This configuration was carefully chosen to ensure an efficient distribution of power across the aircraft, maximizing both performance and stability. The engines selected for the BV-238 were inverted -12 liquid-cooled models, each capable of producing 1,900 horsepower. At takeoff, at higher altitudes, the engines continued to perform admirably, delivering 1,560 horsepower at an altitude of 24,200 feet. This configuration of 6 powerful engines enabled the aircraft to perform impressively despite its massive size, creating a balance of power and stability that was crucial for such a large flying machine. With this 6-engine setup, the BV-238 achieved remarkable performance metrics. The combined power output allowed the aircraft to maintain a top speed of up to 64 miles per hour, a significant feat given its enormous size and weight. Moreover, the aircraft was capable of a maximum combat range of 3,790 miles, which was essential for its intended roles, such as long-range transport and reconnaissance. The power-to-weight ratio was another factor that contributed to the B-52-38's impressive capabilities. With an empty weight of 54,700 kilograms and a maximum takeoff weight of 85,000 kilograms, the aircraft's engines provided enough thrust to handle these substantial weights. The engineering team developed an advanced fuel management system to support the six-engine configuration. The wing structure incorporated dedicated spaces for fuel and oil tanks, enabling efficient distribution across all engines. Similarly, the design included maintenance passages within the wings, allowing crew members to access engines during flight operations. The power system's effectiveness became evident in the aircraft's performance capabilities. At an altitude of 7,375 meters, each engine maintained an output of 1,163 kW, ensuring consistent power delivery throughout the flight envelope. The arrangement of engines along the wing's leading edge not only distributed weight effectively across the airframe, likewise contributed to the aircraft's aerodynamic efficiency. Aerodynamic Innovations. The aerodynamic design of the B-52 represented an intricate balance between conventional principles and innovative engineering solutions. The aircraft's design prioritized both air and water performance, marking a notable advancement in flying boat technology. The wing design of the B-52 was a key feature that contributed significantly to the aircraft's overall performance. It featured a straight, constant chord configuration that extended across the majority of its span, but with tapered outer sections to reduce drag and enhance stability. This wing shape was both innovative and practical, incorporating several pioneering elements that contributed to the aircraft's aerodynamics. With a wingspan of 70 meters and a total wing area of 360 square meters, the design was optimized for lift generation and stability, critical factors given the aircraft's immense size. The wing structure also included an internal catwalk, which allowed for easy access to the engines, an important consideration for maintenance and operational efficiency. An interesting aspect of the B-52's wing design was its integration of auxiliary floats into the underside panels. These floats, which were retractable and could be flushed into the wing surface when not in use, greatly enhanced the aircraft's aerodynamic efficiency. This retraction system reduced drag compared to traditional fixed floats, offering better fuel efficiency and speed. This clever integration of floats into the wing design helped strike a balance between the aircraft's water-based and airborne operations, making it versatile for its intended missions. In addition to the advanced wing design, the hull of the B-52 was a remarkable achievement in hydrodynamics. The hull's length-to-beam ratio was an impressive 8:4, far surpassing the more conventional 6:0 ratio commonly seen in similar aircraft. This optimization of the hull's proportions significantly reduced drag when the aircraft was in the water, allowing it to perform more efficiently during water-based operations. The hull's design incorporated a sophisticated two-step configuration with unique features that improved its ability to glide across the water. The planing bottom of the hull was long and slim, featuring auxiliary steps that further improved its hydrodynamic efficiency. A shallow forward platform, divided into 8 small steps, also played a role in reducing water drag while enhancing lift-off performance. The inclusion of power-operated boat doors was another key feature of the hull design, providing direct and efficient access for loading and unloading cargo. These doors allowed for the swift deployment of goods and troops, increasing the B-52's practical utility in combat and transport missions. The overall design of the hull worked in harmony with the wing structure, as both contributed to the aircraft's ability to minimize both aerodynamic and hydrodynamic drag. This resulted in improved performance, whether in the air or on the water. The stability control system incorporated multiple innovative features. The aircraft demonstrated exceptional water stability traits, capable of operating in sea conditions up to force 5 on the Beaufort scale. The servo control system made the massive aircraft handle like a smaller plane, enabling precise control despite its unprecedented size. The B-52 stability system utilized electronically operated flaps along the entire trailing edge. This configuration provided superior control during both water and air operations. The integration of retractable auxiliary floats into the wing design offered improved stability without compromising aerodynamic efficiency. The aircraft's control systems proved remarkably effective, allowing it to turn on the spot while on water. This maneuverability, coupled with the advanced hull design, enabled operations from rough water surfaces that would have grounded contemporary flying boats. Materials and construction. The B-52's construction primarily utilized all-metal components, centered around a sophisticated tubular steel mainspar design. The hull incorporated a corrosion-resistant alloy specifically engineered for marine operations. The material selection focused on achieving optimal strength-to-weight ratios, essentially balancing structural requirements with performance needs. The material configuration of the B-238 was thoughtfully selected to ensure optimal performance and durability. The wingspar was made from tubular steel, providing the necessary main structural support for the aircraft, while also serving as a fuel storage unit. This dual-purpose design helped streamline the aircraft structure while maintaining its strength. The hull of the aircraft was constructed using marine alloy, chosen for its superior corrosion resistance. This was particularly important given the aircraft's intended operations over both land and water, ensuring that the hull could withstand the harsh environmental conditions it would encounter. To reduce overall weight, the deck structure was made from aluminum alloy, allowing the aircraft to maintain strength without unnecessary weight, which was crucial for both performance and efficiency. This careful selection of materials played a significant role in making the B-238 a groundbreaking design in aviation history. One of the standout features was the two-deck configuration, with the upper deck dedicated to housing the crew and various equipment necessary for the aircraft's operations. The lower deck was specifically designed as a storage area, capable of accommodating up to 150 troops, making it a highly versatile transport aircraft. Additionally, the design incorporated large bow doors, allowing for direct access to the cargo hold for efficient loading and unloading, further enhancing the aircraft's functionality and operational ease. The manufacturing team fundamentally focused on creating a robust yet efficient structure. The wing construction process incorporated passageways for engine access, rather than traditional solid wing designs. The whole manufacturing utilized a two-step design approach with auxiliary steps, creating an advanced hydrodynamic profile. The engineering team developed comprehensive solutions to ensure structural integrity across the massive airframe. The tubular steel mainspar served dual purposes, acting as both the primary structural support and an armored fuel tank. This innovative approach reduced weight, chiefly maintaining structural strength. The structural design of the B-238 was marked by several key features that contributed to its functionality and durability. The wing construction was designed with integrated maintenance access, allowing for easier upkeep and servicing of the aircraft. The hull was reinforced with auxiliary steps, enhancing its performance during water operations and ensuring greater stability when taking off or landing on water. Furthermore, the aircraft was equipped with power-operated bow doors, which not only facilitated efficient loading and unloading, but also provided structural stability during these operations. ensuring the integrity of the aircraft throughout its duties. The structural integrity solutions extended beyond basic construction. The engineering team implemented specialized flaps along the trailing edge, ensuring optimal control despite the unprecedented size. The wing design incorporated additional fuel and oil tank storage spaces, utilizing otherwise empty structural volumes for practical purposes. The manufacturing process, unfortunately, saw limited production. With only one completed prototype, several additional prototypes remained under construction when the war ended. Fundamentally, the B-52-38's construction represented a remarkable achievement in aviation engineering, combining innovative materials with advanced manufacturing techniques to create an aircraft of unprecedented scale. Technical systems integration. The integration of technical systems in the B-52-38 showcased an innovative approach to aircraft control and operation. The engineering team developed a sophisticated hybrid control system that balanced automation with manual operation capabilities. The B-52-38 employed a part servo and part manual control system, building on the successful design philosophy of its predecessor, the B-222. This hybrid control system allowed for the precise handling of such a massive aircraft, offering a combination of power-assisted control surfaces and manual input for ultimate flexibility and reliability. The servo-assisted controls enabled smoother and more effortless manipulation of the aircraft's surfaces, allowing the pilot to manage the aircraft's movement with greater ease. At the same time, the manual override provided the pilot with direct control, ensuring that they could make precise adjustments when necessary, particularly in more challenging conditions or when dealing with the aircraft size and complexity. One of the significant enhancements of the B-52-38 was the integration of power-operated boat doors, which drastically improved the aircraft's operational efficiency. This system enabled direct access to the lower deck, facilitating smoother and faster loading and unloading of cargo. By using power-assisted mechanisms for the boat doors, the aircraft could maintain its structural integrity while handling heavy loads, ensuring that the aircraft remained stable during these operations. This feature not only streamlined the entire process, but also added a layer of operational convenience, as the crew could focus on other tasks without worrying about manual handling of the large doors. The B-52-38's navigation system was another area where advanced technology was employed, ensuring that the aircraft could operate effectively both in maritime and aerial environments. The dual-deck configuration of the aircraft allowed for optimal placement of the navigation equipment, with the upper deck specifically allocated to house all the necessary tools. The crew had access to a full array of primary flight instruments on the upper deck, providing them with the essential data needed to control the aircraft in flight. Additionally, specialized maritime navigation tools were incorporated into the system, allowing the crew to adapt quickly to different operational conditions while flying over water. The integrated control panels allowed for seamless coordination between the aircraft's various systems, enabling efficient multi-role operations and ensuring the B-52-38 could perform its various functions, such as long-range reconnaissance, transport, and bombing, with ease. The communication infrastructure primarily supported a crew of 11 to 12 members, facilitating coordination across the aircraft's vast internal spaces. The system's design notably incorporated unique features for engine maintenance communication, as crew members could access engines through wing passageways during flight operations. The integration of these technical systems required careful consideration of the aircraft's size and operational requirements. The upper deck housed inboard equipment and crew stations, creating an efficient command center for flight operations. Essentially, this arrangement optimized crew workflow and system accessibility. The integration of technical systems in the B-52-38 was designed to support a wide range of operational capabilities, allowing the aircraft to serve in various roles effectively. It was equipped for transport operations, with the ability to carry up to 150 soldiers, making it a crucial asset for troop deployment. The aircraft also had the necessary features for maritime patrol missions, offering extended range capabilities that were vital for long-distance surveillance and reconnaissance over water. Additionally, the B-52's versatile design made it suitable for potential conversion to other military roles, providing flexibility for various strategic needs. The B-52's technical systems demonstrated remarkable integration with its structural design. The wing construction fundamentally supported this integration by incorporating passageways for maintenance access, while the power-operated bow doors represented an advanced loading system that enhanced operational efficiency. The aircraft's size necessitated innovative approaches to system control and monitoring. The engineering team primarily focused on creating intuitive interfaces that could manage the complexity of operating such a massive aircraft. The control systems designed notably balanced automation with manual control, ensuring reliable operation under various conditions. Performance analysis. Performance metrics of the B-52 demonstrated remarkable capabilities across various operational parameters. The aircraft exhibited exceptional versatility in both maritime and aerial operations, setting new standards for flying boats of its era. The speed performance of the B-52 was impressive across various conditions. At sea level, with a weight of 60,000 kilograms, the aircraft could reach a speed of 350 kilometers per hour. As the aircraft ascended to an altitude of 6,000 meters, it maintained a higher speed of 25 kilometers per hour, while still carrying the same weight of 60,000 kilograms. During landing, the aircraft's speed was reduced to 143 kilometers per hour, allowing for a controlled and efficient approach to the runway. The aircraft maintained stable flight characteristics up to its service ceiling of 7,300 meters. Essentially, these performance figures were exceptional considering the aircraft's massive size and weight. The payload capacity of the B-52 was a remarkable achievement in terms of optimization, with a maximum takeoff weight of 85,000 kilograms, or 187,393 pounds, and an empty weight of 54,700 kilograms, or 120,593 pounds. The aircraft was engineered to carry substantial loads. The wing loading was 261 kilograms per square meter, or 53 pounds per square foot, further emphasizing its ability to support heavy weights. This payload capacity enabled the B-52 to transport up to 300 troops, making it a highly versatile military transport aircraft. In addition to personnel, the aircraft was designed to carry up to 20 to 150 kilogram bombs, showcasing its capacity to handle a variety of military armaments. These features collectively made the B-52 a versatile asset, capable of fulfilling multiple roles in a military context. The B-52's range capabilities set new benchmarks for aircraft of its era. Operating at an altitude of 2,000 meters, the aircraft achieved a range of 620 kilometers, while maintaining a cruising speed of 365 kilometers per hour. This impressive range was achieved with a total weight of 92,000 kilograms. The endurance calculations for the B-52 took into account several operational parameters to ensure its efficiency. These included the optimal cruising conditions at medium altitudes, which allowed the aircraft to achieve its best performance. The fuel consumption rates were also considered across various power settings, ensuring that the aircraft could operate efficiently under different conditions. Additionally, weight variations throughout the flight envelope were factored in, accounting for the changes in weight as the aircraft loaded and unloaded cargo, which could affect its overall endurance. In addition to its primary range capabilities, the BV-238 demonstrated exceptional operational flexibility through its ability to land on water. The landing speed of 143 kn divided by h enabled safe water operations, whereas the wing loading characteristics ensured stable flight across various weight configurations. The performance envelope expanded through external payload options. The aircraft incorporated pylons capable of carrying either for torpedoes, for 1,000 kg bombs, and for HS-293 anti-shipping missiles. The BV-238's performance metrics validated its design objectives, establishing new standards for large-scale aircraft operations. The combination of range, payload capacity, and operational flexibility positioned it as an exceptional achievement in aviation engineering. Engineering legacy. The engineering achievements of the BV-238 fundamentally shaped future aircraft design, establishing benchmarks that influenced aviation development for decades. As the heaviest aircraft of World War II, with a weight of 110 tons, the BV-238's design solutions continue to resonate in modern aviation engineering. The BV-238's innovative approach to size management essentially created new paradigms in aircraft design. At length, its wingspan of nearly 200 feet established principles for managing large aircraft structures that would later influence post-war aviation development. The engineering team solutions for weight distribution and structural integrity created lasting impacts on aircraft design methodology. The design of the BV-238 left a lasting legacy, influencing several aspects of modern aviation. Its tubular spur design set the foundation for structural efficiency, inspiring future aircraft designs that prioritize strength and weight distribution. The two-deck configuration became a key reference for modern transport aircraft layouts, offering enhanced space utilization and operational flexibility. The wing access systems introduced in the BV-238 influenced contemporary maintenance approaches, enabling easier and more efficient servicing of large aircraft. Additionally, the aircraft's hull aerodynamics advanced seaplane design, laying the groundwork for improved performance in water-based operations. Several technical innovations from the BV-238 have proven to be enduring and valuable. In the evolution of aviation, the tubular spur design, which served both as structural support and fuel storage, set a precedent for more efficient and streamlined aircraft designs. The advanced understanding of wing sweep and its effects on transonic drag reduction became a key factor in improving the aerodynamic performance of future aircraft. Additionally, the sophisticated hull design of the BV-238, with its length-to-beam ratio of 8:4, was a significant departure from the conventional 6:0 ratio, offering enhanced hydrodynamic performance and influence in future seaplane and amphibious aircraft designs. The aircraft's design philosophy fundamentally influenced the development of the Hughes- for Hercules. Analogous to how modern aircraft incorporate similar principles of structural efficiency and payload optimization, the BV-238's capacity to carry 300 troops demonstrated load management solutions that would later become standard in large transport aircraft design. The development of the BV-238 provides valuable lessons for modern aviation engineering, showcasing several enduring principles that remain relevant today. The design process, which began in 1940, highlighted the adaptability of the aircraft's design, transitioning successfully from commercial to military applications. This adaptability was further demonstrated by the integration of alternative power systems when the originally planned engines became unavailable, ensuring the aircraft's continued progress. The aircraft also incorporated significant structural innovations, such as the use of corrosion-resistant alloys to withstand the harsh conditions of marine operations. Additionally, the development of integrated wing maintenance access systems allowed for more efficient upkeep and servicing, a crucial factor for operational readiness. In terms of performance optimization, the BV-238 achieved impressive metrics, including a top speed of 25 km per hour at 6,000 meters altitude. It also demonstrated an exceptional range capability of 6,620 kilometers, all while maintaining a practical payload capacity. The engineering team's approach to solving complex challenges remains relevant today. For instance, their solution to the asymmetrical arrangement demonstrated that unbalanced forces could be neutralized through small rudder deflections, a principle still applied in modern aircraft design. The BV-238's innovative features extended beyond basic structural elements. The aircraft's sophisticated hull design, with its optimized length-to-beam ratio, resulted in substantial drag reduction. This hydrodynamic efficiency breakthrough continues to influence modern seaplane design. The integration of multiple roles into a single airframe from transport to potential bomber configurations demonstrated versatility principles that modern military aircraft designers still pursue. The aircraft's ability to operate with a crew of October 12 members showcased efficient crew management solutions for large aircraft operations. The BV-238's engineering legacy is particularly evident in its approach to maintenance accessibility. The incorporation of wing passageways for in-flight engine access represented a forward-thinking solution to maintenance challenges, a concept that continues to influence modern aircraft design. The aircraft's structural solutions for managing its unprecedented size established fundamental principles for large aircraft design. Its empty weight of 54,780 kilograms required innovative approaches to weight distribution and structural integrity that would later inform the development of modern heavy transport aircraft. The engineering team's understanding of advanced aerodynamic principles, particularly regarding wing sweep for transonic drag reduction, preceded similar discoveries by allied engineers. This knowledge, essentially rediscovered by Western engineers after the war, demonstrates the advanced nature of the BV-238's design philosophy. The BV-238 is a striking example of German engineering during World War II, pushing the limits of aircraft design with its 110-ton weight and 60-meter wingspan. Its innovative features, such as the advanced hull design, 6-engine configuration, and dual-deck layout, set new standards for large aircraft development. The aircraft's design, capable of transporting 300 troops over 4,110 miles, left a lasting impact on aviation engineering. Although only one prototype was built, the BV-238's legacy continues to influence modern transport aircraft, particularly in structural integrity, size management, and maintenance. What do you think were the most innovative aspects of the BV-238's design? Share your thoughts in the comments below. If this video makes you happy, please like the video. Thank you for watching the video.